It's Akila.
This is Roshni.
Today we are here to present our term project, which is ACIC Admission Control Instruction Cache. So explains the outline of our presentation today. We start with introducing the ACIC implementation details and show the result analysis, and we show further how much our project can be improved. So, going to the introduction, ACIC is a cache replacement policy which is targeted on the instruction cache for handling issues with server workloads, which exhibit both spatial and short-term temporal localities. That is, they have long bursts of data followed by small short bursts. Handling such data sets will be an issue with the regular LRU replacement policies, which consider only the spatial localities. To handle the short-term temporal localities which come in between, there has been a concept of I filter which was proposed, but that is not efficient, as in some cases it might still cause cache pollution. Hence, a control mechanism is required. The ACIC proposed here is a combination of control mechanism, which is the temporal locality predictor, plus the I filter. The ACIC replacement policy uses the cache burst history instead of the cache access history. Seeing the jargon here, let's delve into the details of the I filter. The implementation or the hierarchy of the memory system looks with the insertion of the I filter. An I filter is a 16-entry full set associative buffer. So when an instruction address arrives, the block is checked parallelly in both I filter and I cache. And if the block is found either in the I filter or in the I cache, it is sent it is considered a hit and it is sent to the CPU. If it is not found, then we fetch the instruction block from the L2 cache and place it in the I filter. Now assume that the I filter is full. Then this instruction block will evict a block, and this evicted block is now in confusion as to whether it needs to be evicted completely or it needs to go into the I cache. So we are not sure if this particular evicted block will be accessed soon in the near future or it is accessed very far from the near future. So this particular evicted block, whether it needs to be inserted into the I cache or not, it is decided by the control mechanism. So this evicted block, if it has a less reuse distance, then it is inserted in the I cache, else it is thrown away. So which means it has higher reuse distance, it is thrown away, and with less reuse distance, this particular evicted block is inserted into the I cache. Now, what is this admission predictor which decides this control mechanism? So, the evicted block tag is sent to a hash function which gives the index of the history register table. And the bits in the history register table point to the pattern table, which has a counter whose threshold will indicate when the block is to be thrown away or placed in the I cache. So, how do we update this particular block? This particular HRT and the pattern table. Let's delve into the details of this. But before that, let's look into the I filter and I cache and get clear with some concepts. So when an instruction block is placed in the I filter, a I filter victim block is evicted out. This particular block can be thrown away or placed in the I cache based on the control mechanism. Let's assume that this particular victim block is placed in the I cache. Then the I cache has to evict the contender block for this. So this particular I filter victim block will have a tag and the contender block will have a tag. These two tags are stored in the comparison status handling register, which has 4 entries, which is I filter victim block tag, the contender block tag, the is valid bit, and the LRU bits. So we look for the valid bit where it is 0 and insert it. And the LRU bits of this particular block should also be the minimum value. And the iFilter tag and the iCache contender tag are inserted here. Now, when a new address arrives, it is compared with the iFilter victim tag. If it matches the iFilter victim tag, then the HRT bits will be left shifted by 1 and the pattern table will be incremented by 1. And the is valid bit will also be made to 0 and the LRU bits will be incremented by 1. If it matches the iCache contender tag, then the HRT bits will be left shifted by 0 and the pattern table will be decremented by 1. Here we are making the valid to 0, stating that this particular entry which has been placed in the CSHR has been resolved, and that particular entry can be used for further replacement if there are new tag pairs coming up. Now mapping this to ZSIM, we see that the original filter cache implementation which was there has been modified, and it's now used only to generate the access request. The filter cache implementation for the data cache has been left untouched, and the access request generated here goes parallelly to the iFilter and the iCache. Let's moving on to Roshni.
Okay, so now let's understand the code flow. So there are 4 major files that we have used in this project, which is oocore.cpp, filtercache.cpp, cache.cpp, and acic.h. The oocore.cpp is a file where we have modified it to create admission predictor logic. It also generates access requests to filter cache. The filtercache.cpp generates access request to IFL, which is our iFilter cache. And the cache.cpp is implemented. It implements the logic of parallel access generation for searching both the iCache and the iFilter. The ACIC.h implements the admission predictor and the predictor logic. Now let's look into the result analysis. So for our project, we have run different configurations, and this particular graph explains the original cache configurations. Here the x-axis represents the benchmarks that we have tested, and the y-axis represents the program parameters, which in this case is IPC and MPKI. The results are characterized as no IFL, which signify the benchmark outcomes calculated without utilizing the iFilter and filter cache. The ACIC benchmarks represents results computed with ACIC. The no ACIC benchmarks denote results calculated without employing the admission predictor, relying solely on the iFilter. All the MPKI graphs that are plotted here are plotted on a logarithmic scale on the y-axis. This is because to include the smaller data sets as compared to the server benchmarks. We find that the LRU replacement policy works better than ICSC and the bypassing policies. This simply implies that there are fewer data bursts within these benchmarks and a lack of obvious spatial temporal localization. To emulate an environment and to replicate server benchmarks, we have downscaled the iCache sizes. This alternation is intended to increase the frequency of cache block replacements. Now let's look at the small cache graph. So after the changes, the results that we've observed in this graph are the MPKI values of the LRU are still better, proving that all of these benchmarks have good recency friendly access patterns. There are certain spec benchmarks such as the one that is shown in the next slide have almost similar performance with ACIC, bypassing policy and LRU replacement policies. Hence, we thought that by changing the number of entries in the HRT, which is history register table, pattern table, PT, CSHR, comparison status holding registers, we could achieve better results. So thus we have changed some configurations. So in the figure stated, the cactus ADM has the closest MPKI value in all the 3 cases, which makes us to assume that this benchmark is accessing the cache more frequently and has less recency cache access pattern than the others. So if we can decrease the iCache size further, then ICSA could have shown better improvement for this benchmark. So our project has been implemented and has been simulated for all these different values of HRT, PT and CSHR. So the ACIC replacement policy is implemented on both the spec and the PASIC benchmarks, and we were able to obtain a speed up of 1.007, which is achieved over LRU, while the expected was 1.02 compared from our reference paper. So talking about the future scope of this project, we could not implement the QEMU emulator because we were not able to, we faced problems while installing this emulator. So if we had QEMU emulator, we would have obtained the trace files which could have run on a ZSIM simulator. So the MPK results could have been achieved as expected, as we needed to run on the server benchmarks. Thank you.
Thank you.